Okay, good afternoon, everyone. Thank you very much for attending today's webinar of Computational Social Science Laboratory at the Chinese University of Hong Kong. My name is Ling Zhu, and I am an assistant professor of sociology here. I will be the moderator of today's talk. As you can see from our poster, today we are very happy to have Dr. Linda VECGAILE as our speaker. I hope I pronounced the last name correctly.
Perfect.
Thank you. Dr. VECGAILE is currently a research scientist at the Max Planck Institute for Demography Research, Department of Digital and Computational Demography in Germany. Her research actually brings in the strengths of computational social science and demography research. And her research focuses on adapting natural language processing models to predict life course sequences so as to offer insights into individuals' familial and career trajectories. And her work also explores the broader implications of these patterns for social inequalities and policy development. And therefore, her talk will definitely fit our major topic about computational social science because it brings the strengths of computational techniques and social science research topics. Without further ado, I will now turn the table to Dr. VECGAILE. Let's welcome.
Thank you so much, and hello everyone, and thank you for the kind introduction. And I must say I'm very excited for this opportunity to present at today's webinar. And yeah, thank you for inviting me. And so yeah, I'm Linda VECGAILE, and today I'm going to present you a study that I'm doing together with my colleagues. I would like to shortly introduce them to you. It is Alessandro Spata, who is an independent researcher. He has joined also the talk today. Then another collaborator is Luis Felipe Vecchietti, and he is a research scientist at the Max Planck Institute for Security and Privacy. And then another collaborator is Emilio Zagheni. He is a director at the Max Planck Institute for Demographic Research. And in this project, we are developing a model capable of predicting life course sequences. And when I talk of life course sequences, we are focusing on life course events such as employment, unemployment, people involved in education, caregiving activities, or transitions to retirement and other similar social employment states. And to develop this model, we are relying on the life course theory. And the life course theory argues that individuals' lives unfold as sequences of interconnected events, where the timing and order and duration of these events can shape the subsequent life course trajectories. So for instance, transitions like moving from education to work can have a substantial impact on our future lives. For example, if we experience smooth transition from school to work, very often it translates into stable employment trajectories in the future. While if we experience, for example, insecure job during this phase of life, insecure job transitions, then it may have a negative, long-lasting effect on future career development. And in literature, it is often referred to as the scarring effect. And then there are also other events in our lives that can impact our future career and life trajectories, such as, for example, childbirth or caregiving activities and the like. And so if we think about our life as a sequence of these interconnected events, where something that happens to us early in our lives can influence what will happen to us later in our lives, it actually bears a resemblance to words in a sentence, because just as words within a sentence are arranged in a specific order, which is based on certain rules and logic and influenced by surrounding words and sentences and the overall context, very similarly, also these events and phases in our lives are similarly structured. And there is also a certain logic, right? And these events are interconnected, and what happens to us earlier influences what will happen to us later. And so by drawing this analogy between events in individual's life towards in a sentence, we seek to adapt natural language models based on machine learning algorithms, and to identify these underlying structures and patterns in individuals' lives, just as it is identified in languages, in sentences, and to use these models to actually predict life course sequences. It is just like when you use, for example, Gmail, and you start, or any other algorithmic tool that helps you to finish a sentence. It often offers you the next word that is most likely for you to use, or even help you to finish the sentence, or it's actually similar to ChatGPT. So we are trying to apply this logic, but to people's lives. And in order to model this thing, we are using transformers. And it is a type of neural network architecture which has been specifically designed for sequence-to-sequence tasks, such as language translation and text generation. And the interesting part about this algorithm is that it has the so-called self-attention mechanism, which allows to attribute weights to these words in a sentence, and this enables the model, the algorithm, to identify these long-range dependencies between words. And as we define that life course sequences is also a sequential data, where each year's state is dependent on the previous year's state, we assume that transformers is very suitable for modeling these life course sequences. And let me, in a very short and simple way, explain to you the main logic, intuition behind how this model works. So again, we are treating an individual's life as a sentence. And here we have a sentence which consists of year of person's age from 18 till 60. And here, every year, what happens to an individual each year can be taken as a word in a sentence. So here, individual is engaged in educational activities from the age 18 to 22. Then the person transitions to employment, then experiences a spell of unemployment, and so on. And in our study, in our project that we are developing, our goal is to use this sentence in the following way. We want to use information about the individual from the age 18 till 55, and then predict what will happen to the individual in the last 5 years of this period that we are observing. And how we train the model is we take this sequence from 18 till 55, and then we tell the model, so when you see this sequence, which consists of employed, then there is a spell of unemployment, and there is a spell of unemployment, and etc. When you see a sequence of this type of event, please know that the next most probable event that will follow at the age of 56, which we want to predict, is marginal employment. And always when we want to know the next state, we need the previous, these 38 years. So then again, if we want to train the model to predict what will happen at the age of 57, we again take the preceding 38 years, and we again say, so when you see this sequence, know that the next state that will follow will, again, in this case, be marginal employment, and so on. And then when we do the actual prediction, when we have trained the model and then we ask it to predict, how it works is that we just give this information about the individual, and then we ask it to predict. So then the state is predicted. Then we use the predicted state, and we include it into our preceding sequence that we need to know in order to guess again the next state. And then iteratively, we are predicting year by year, and in the end we have a prediction of this 5-year sequences. So very shortly, in a very simple way, this is how we have been working. And so in order to train this model, you need a lot of these individual sentences, these individual sequences. And in our case, we rely on registered data that comes from German statutory pension insurance. And this is the data that includes individual level biographies. And we have in total over 200,000 individuals that we can use in order to develop this model. And when we build our data, we rely on these 11 social employment states. So we want to predict these 11 events that can happen to an individual. And so these events are like a person is doing a school education, or a person is unemployed or marginally employed, or full-time employed, or a person transitions to insurance and other social employment states. And then in addition to these 11 states, we also use information about individual's gender, age, and the year when the event has been observed. So I want to stress and underline that in order to build this model, we use very limited data. We want to build this model as simple as possible for the starters. And when we train the model, we use data from individuals born between 1940 and 1957. And then very often when we build this, like when these kind of models are built, people would ask a question, but how would you know that the model captures that there is some change over time? Because life course sequences, they change from generation to generation, from year to year. And how do we prove that the model is actually able to capture these dynamics? And in order to do that, when we test the model, we test it not only on individuals born during the years that the model has seen in its training phase, but we add also years that when individuals were born that the model hasn't seen. And if we get good predictions also for these individuals, we can say that, yeah, actually our model is also very good at generalizing on unseen information. And one of the very exciting and, in my opinion, key advantages of transformers is that when we do predictions, rather than predicting one single outcome, we can actually predict, we can actually get a probability distribution of all possible states that an individual may experience at the specific age that we are trying to predict. So say, for example, here. So in our case, in our project, we are trying to predict the sequence from the age 56 to 60. And this is an example of one individual. So for example, this individual, let's assume that we try to predict only 3 states. Either individual will become employed, unemployed, or retired. And in this case, for example, at the age of 57, we see that there is 50% of probability that a person will be employed. However, we also see that there is a 40% of probability that the person will actually be unemployed. And this is very, very interesting and important information because it gives us a more nuanced view of these human future trajectories. Because knowing these probability distributions, we can actually measure how confident we are about the sequences that we are predicting. And in order to summarize this probability distributions and this information, and to measure actually how certain we are about the predictions that we make, we are using entropy. And entropy measures how spread out or concentrated these probabilities are that we are acquiring. And here is, for example, an example. So in this case, individual that we have been discussing, so for example, at the age of 57, the probability of being employed is 50%, but being unemployed is equally high. So it is actually very uncertain whether this person will be employed or unemployed, because these probabilities are very similar. And if you use entropy, in this case, entropy will be very high for this particular case, meaning that we have greater uncertainty. However, if we look at another example, for example, here, individual at the age of 56, the model predicts that this person will be employed with 90% of probability, while probabilities of being unemployed or retired are very low. It's 5% for each. And in this case, these probabilities are more concentrated on one social employment state, which means that the prediction is more certain. And in this case, entropy measure will be low. So then we can summarize this entropy over the 5-year period to have the average measure of how certain or uncertain prediction of this person's sequence is. And here we can see that when the entropy is high, the confidence of the overall predicted sequence for this individual is low. So we should be very careful with actually doing something with these predictions. Or in the other example, the entropy is very low, which means that the sequence that we have predicted, it has actually quite high confidence, and very likely that this is what will happen to the individual based on this individual's preceding life course history. And now we want to see, to summarize, so how well actually our model works on our data that we are trying to predict and model. And this plot shows that this is a frequency distribution of this average entropy per individual. And we see that for the majority of individuals, the average entropy index is rather low, which means that the sequences that we are trying to predict are actually quite predictable, which is good news for us. And another thing that we are doing in our project is so we want to make sense of these predicted sequences and then somehow organize them and arrange them. And the idea that came to our minds is that we could actually take all the individuals that we are analyzing, and we want to group them into clusters based on this sequence that we're trying to predict from the age 56 to 60. We want to see what are the main patterns of this life course period, like in general, what people tend to experience, what kind of sequences, patterns they tend to have during this life period. And then when we have these clusters, these groups, we want to see which groups our model is better at predicting. So which groups the model can predict best, which groups model struggles to predict, or alike. And in order to do this, we use a sequence analysis method. And in order to estimate, to evaluate which life course sequences are similar, which are less similar, we use the optimal matching method. And then in order to cluster these individuals based on how similar these life course sequences have been calculated, we use hierarchical clustering using Ward's method. And so we get a type of a tree, a dendrogram, and then we can see what are the major clusters, major groups, and then we can decide which groups we are selecting, which groups are the most relevant. And before we jump into analyzing these actual groups that we identified and to evaluate how well our model works, let me also quickly mention that in order to evaluate how well our algorithm works, how well it predicts, we also wanted to compare it to other methods. And we decided at this stage to compare them to methods that are commonly used in sociology literature when people are dealing with life course sequences. And one of the methods is Markov chains. And this is a technique that lets you to predict the next state, let's say in individuals' lives, but based on the current state that you are in. And because of that, this is a big disadvantage for Markov chains, because we cannot consider more distant future life course trajectory, because as we discussed at the beginning of the presentation, it is very important to consider what happens to you earlier in your life, not only, let's say, this year. However, this is still a method how you can predict life course sequences, and this is a very valuable method, and we use it for comparative reasons. And then another method that we are applying is a simple carry forward model. In this case, we're just simply taking the last state at the age of 55, and we freeze it, and we assume it that this state will remain constant for the next remaining 5 years. And this is a simple method. However, it has shown to actually work quite well. So let's see how it works in this case. And here we start seeing the clusters that we have identified. First, I will just quickly run through all the clusters that we have identified. And I don't know how I can... I will show you the main clusters, and then I will show you the evaluation that we carried out. So the first cluster are individuals that tend to be employed for the majority of time in their life course, and then during the 5 last years of the period that we are observing, they tend to remain in the employment. Then the second cluster is individuals who are engaged in professions or occupations that are not covered by the statutory pension insurance. Those are individuals who are working, who are doing a job that has some specific private type of pension insurance. And these individuals tend to switch to this employment in their late 30s, late 40s, and then they tend to stay in this occupation for the remaining period of our observation. Then cluster number 3 are individuals who tend to enter unemployment in their early 40s, late 50s, and then they tend to remain in this unemployment state. The fourth cluster are people who tend to start marginal employment in their late 40s, early 50s, and then again, they tend to remain in this marginally employed state until the end of the observation period. And cluster 5 are people who tend to retire early. The yellow indicates people who are receiving pension insurance, and then also people who are engaging in childcare or family care activities. And this is the cluster number 5. And cluster number 6 are people who are doing other activities that haven't been specified in these social employment state categories. We see again like a similar dynamics. First they are employed, then they switch to this another unspecified activity, and then they tend to remain in this activity. And now I would like to pick a couple of most interesting clusters, and I will analyze a few of these clusters. I cannot cover them all because of the time limit, but yeah, these are that I found the most interesting ones. So the first one is the cluster number 1, which we already saw, and this cluster comprises most of the individuals in the data. So we have the data, and in this data, more than 66% of all individuals, they belong in this cluster. So it's one of the most important and biggest groups. And we see that for this group, yeah, the majority is just being employed, and then they remain employed. And when we compare, so these are the actual social employment states here that we are trying to predict. And this is how our predicted social employment states look like. They are not perfect. However, the model has captured the main pattern. It has identified that these individuals are most likely to remain in employment. And what is interesting is that this entropy index that we are using in order to determine how confident our predictions are. And in this case, this entropy index is quite low. And it signals that it is very likely that we can be very confident about the predictions that we have generated for these individuals. And we see that our model predicts accurately at the 90% of the time, which is rather high and very good result. However, very interestingly, the very simple carry forward method that I described earlier, that just freezes the last state and then assumes that it will remain constant for the next 5 years, is actually performing equally well. I will discuss the implications of this finding in my later slides. And then if we compare it to Markov chains, this model unfortunately performs very poorly. So now let's take a look at the cluster number 3. And this cluster is actually more interesting because in this case, we see individuals that are most likely to remain employed. So we wouldn't worry too much about these individuals because the whole goal of this project is to be able to predict life course sequences for individuals and then identify which individuals are in a situation which is not favorable for their lives, for their future lives. For example, if they are at risk of becoming unemployed or disabled, if we can predict that these individuals will experience some difficulties in the future, we can do some preventive measures in order to help them not enter these unfavorable social employment states. And well, for example, here, individuals are predicted with high certainty that they will remain employed. We are happy. We don't have to do anything about that. However, this group, it is relatively small. It is only about 5% of the whole data. However, these are individuals which we really care about because these are individuals who are actually entering unemployment. And if we would be able to predict that these individuals will remain unemployed for the next 5-year period, we can preferably do something about that. So let's see how well our model performs in order to predict these life course sequences. And we see that, again, these are the actual observations, and these are the predicted ones, the predicted sequences. And we see that, again, predictions are not perfect. However, the most important thing is that the model captures this dynamics, this pattern, that these individuals will remain unemployed. And we see that the model predicts with 65% accuracy. It's not high, but still it is normal. Let's say I'm satisfied with these predictions because if we look at the entropy measure, we see that it is relatively high. And it means that it is quite difficult. It is challenging to predict life course sequences for these individuals because it means that although the model shows that the most likely outcome for these individuals is to remain unemployed, actually there are also other alternative scenarios that can happen to this individual as well, which can be more favorable or even less favorable. And given that we have these probability distributions, we can actually see what is the second most likely event that can happen to this individual. And in this case, given that the entropy measure is quite high, the second most likely event that can happen to an event is also quite probable, quite high. So if we see at the second most probable event that can happen to an individual based on their preceding life course sequence, we see that actually there is a high probability that these people actually may be also employed or even just at least marginally employed, which is very good information for us, because using these probability distribution and these uncertainty measures, we can see that if we target these particular individuals who have, let's say, equally high probability of remaining unemployed or actually switching to employment, we could ensure that they have more stable career trajectories. And this period before mandatory retirement age, which is around 55, 65 or 67, it is very important that individuals stay employed, because then they can accumulate more financial security for their retirement age, and it is better for individuals than to stay involuntarily unemployed. And a very similar pattern can be observed also for cluster number 4. And these are individuals who tend to enter marginal employment at their late 40s, and they tend to remain in this marginal employment state. And again, if we look at the average entropy measure, we see that it is again relatively high. So what it suggests that although the model predicts that the most likely state for these individuals is to remain marginally employed, there are also other social employment states that are very likely to happen for these individuals. And if we take a look at these other probable social employment states, we see that if we would apply certain measures, certain policies in order to help these individuals with some financial contributions to do maybe some education or retraining or something to help them improve their labor market conditions, we could actually do that, because the second most probable state for these individuals is to be employed, which is very, very interesting, information to have. Yeah, because to mention again, it can help develop more targeted policy interventions in order to prevent already to have more targeted interventions to help these people not to enter these unfavorable social employment states. And now let's talk a little bit about the implications for the life course theory of these findings that we have developed and found. So first of all, what does it say when we have this simple carry forward method that freezes the last social employment state and carries the same event all the way until the end of the observation period? What does it say if this method performs equally well to our sophisticated transformer models? So the first conclusion is that actually it just means that life course states tend to be very stable during the ages from 56 to 60. And this aligns very well with the life course theory, because it states that there are certain life phases, such as late career or pre-retirement period, when individuals tend to exhibit relatively stable life course sequences, especially for those people who are in stable employment or they have well-established routines. However, it also stresses the fact about this path dependency and inertia, which means that past experiences, especially the recent ones, it shows that they strongly shape future trajectories, which can be both good and bad thing at the same time, because if people who tend to enter unemployment at the age of 55, it is actually very unfavorable for them if, according to these theories and how life evolves, it is very likely that they will actually remain unemployed, while individuals who, so for this type of individuals, this path dependency and inertia, it is very bad news, while individuals who have been employed and then they also remain employed at that period, they are very likely also to stay employed for the future period, which is good news for these individuals. So this is very interesting fact to think about, how our lives actually work, and that people who tend to enter one trajectory, it is actually very difficult to get out of this trajectory. And it is good if you are lucky enough to have a good trajectory, stable life course trajectory, because you are more likely to stay on this stable and favorable life course trajectory. Well, it is very bad for individuals who are less lucky and who do not have, who do not have this favorable life course conditions, and it is very difficult to get out of these conditions. And this is very well shown with these methods, which actually shows that it doesn't even matter so much how your life course looked before the age 55, because just having your social employment state at the 55, you can very well predict what will happen to you in the next 5 years. And this is a little bit scary if you think about it. And then, so the challenging question is, so what do we do about this? Does it mean that complexity may not actually add value to our model? And what I can say is that in cases where life course states are relatively stable, more complex models like transformers may not provide a significant advantage over simpler approaches. This suggests that for certain age ranges or life phases, simpler methods might be sufficient for predictions. So if you want to predict what will happen to an individual between ages 55 to 60, it is enough just to know what person did at the age of 55, and just by carrying forward the state, you are around 60-70% of accuracy, you will achieve good results. However, here also I need to underline and remind that when we are using our transformer model, we use very little information about individuals' lives. Let me remind you that we just use age, gender, year of observation, and then these 11 social employment states. Because there is actually so much that is happening in individuals' lives. Person may become disabled or have health issues, or it very much matters what type of profession you are having, what type of education you are having. All these aspects determine also a lot how your life will evolve. However, we are not using this information, and yet still our model predicts relatively well. However, if we think about transformers, why actually it outperforms simpler methods is that it provides this probability distributions for each state that we are predicting for each age, because we can assess not only the most likely outcome at the particular age or period of age, we can also see the likelihood of alternative scenarios, which is very important information to have. And by looking, for example, if a person is employed and has a probability of 90% remaining employed, we can be fairly confident that, yeah, this prediction is stable. While if the person is predicted to be employed with 50% probability and unemployed with 45% probability, it indicates that there is a higher level of uncertainty in these predictions, and there is a potentially very high risk of this person entering unfavorable social employment state. And this is something that simpler method cannot do. And if we have this additional information, it enables us to prepare more targeted, to do more targeted planning and provide more targeted support for these individuals at risk. And regarding the limitations of our model and our study, of course, when it comes to machine learning algorithms, there are many limitations, starting from the classical one, the black box nature of machine learning algorithms is that you cannot really very clearly interpret these predictions, because algorithm doesn't show you explicitly what kind of mechanisms it has identified, which led to these particular predictions. We don't have those, so this is a limitation. However, at this point, we can't really do anything about it. Another very classical limitation is that if we are training our model on biased data, because data usually includes the social biases, we are most likely replicating these biases. So this is something that also we haven't figured out yet how to deal with it. But these limitations that I enlisted in these slides, this is something that maybe we can actually do something about that and take pay more attention to these limitations. So first is that there is a dynamic changes in demographics. So as social norms, policies, and economic conditions evolve, the model's predictions may most likely lose accuracy if not updated regularly. So what you can do, you need to ensure that you are retraining this model every time you have new data available. And also, together with this comes an aspect that if we have trained our model on German data, it doesn't necessarily mean that we can use the same model and apply it, for example, for China society, because people in China might have different patterns in their life course sequences. There are different norms and different traditions. So for each country, I assume we would need to train a separate model. So yeah, this model is not generalizable, let's say. However, I haven't tested it, and I cannot guarantee that this is the case, but this is a risk. Then, of course, there is an uncertainty in long-term predictions, because the further out the prediction, the more years we try to predict, the higher the uncertainty, which limits the reliability of forecasts over longer time frames. However, this is again something that you can test. You can try to predict 5 years, then you can try to predict 10 years, 15 years, and see how well model predicts, and then try to understand whether this model still works or it doesn't work at all. And then, of course, data quality dependency. The accuracy of predictions is very much limited to the quality and completeness of the data that you have. And for sure, the more data you have, the better is the data, the more likely that you will develop a better model that is better at predicting outcomes with higher certainty. And then there are ethical concerns. Because let's say we are predicting these individuals who are unemployed in the future, and we want to make these targeted interventions. So we might decide, okay, we will do a targeted intervention for all individuals that has, let's say, over 50% of certainty, which means that people who have lower uncertainty, let's say 45%, they will be excluded from this advantage to receiving some sort of supportive treatment to help them avoid potential risk of, let's say, becoming unemployed or exiting unemployment. And so yeah, if we have these individual level results, and it is up to us to choose which individuals will receive treatment, which not, it can create some sort of stigmatization or discrimination, and we must be very careful with this aspect. And this is where I finish my presentation, and yeah, I hope you enjoyed it. I hope I managed to present the main idea of our project, and I'm very, very much looking forward to your questions, and I'm happy to clarify whatever was not clear to you. Thank you so much for your attention.
Okay, thank you, Dr. VECGAILE, for this great talk and very innovative application of use transformers to predict life course sequences or events. Now the floor is open to accept questions, and there are two ways that you can indicate that you want to raise a question. One is if it is okay for you, you can just input a brief message in the chat box to indicate that you have a question, and I will cue you to ask a question by yourself. If you are not very convenient to speak by yourself, you can also input the questions in the chat box and I can read your questions for you. So now the floor is open. Is there any questions? Is there any questions from the audience?
Yes, I have questions.
Oh, okay. So the question is from Liu Yongye. Yes,
Yeah.
please.
Thanks for your presentations. I have some questions. For the first one, you are using the sequence analysis, but I'm not very sure that about what is your input in the transformers. Whether your sequence is equal length sequence or unequal length sequence. And some sequence in typical sequence analysis, you may deal with the missing value issues and sensor issues. So if you are using the equal length sequence, you may ignore these issues. But in machine learning algorithms, you may use include these missings and the sensor state. And this is the first of my questions. And if your but I'm still unsure that what is your input in your transformers and what is your output. Because if in sequence analysis, usually we are calculating the dissimilarity matrix, and I'm not sure that is your whole sequence is in your transformer is the input or the dissimilarity matrix is your input in transformers, and what is the output in your transformers. For example, you are presenting, you have 6 clusters, and you have predicted the later 5 years of their status, but I'm not sure that your output is the whole sequence for each individuals from their 18 to their age 16, or um, your output is only the later states, which means you clarifying you have 10 states of your sequence. I'm not sure what is your output. And the last question is, you have already defining your state into 10 categories. So how about extend your states, for example, combining another state, for example, the family informations, or using the multi-channel sequence analysis, what's the implications can your methods apply or generalize to this kind of sequence analysis method? Thank you.
Thank you so much for your questions. So regarding your first question about the length of the sequences, to simplify the way how we build our model and to simplify the way how to analyze it, we decided that we will use only sequences of equal length. So we take in our data only individuals for whom we have observation period from the age of 18 till 16. And when we apply sequence analysis, so we don't have issues with missing values or truncation or all sequences are the same length. So it makes the analysis much more easy. And regarding the what is the output of what is our output? So the output. So how to say? We are using the input is a sequence from the age 18 till 55. So everything that happened to this individual in this period, we use this information to predict what will happen at the age of 56. And this information that we use is exactly as you mentioned. We have these categories, these 11 categories of different social employment states. And then in addition to that, we have age, and we also know the year at which this observation is happening. So you use this information in order to predict the next step. So that is the output. And then you can predict each next output iteratively. You always take the preceding 38 years, which is our input, in order to predict the state at the time point 39. And regarding your question about what about other information that you could include into this model, into this prediction, yeah, it depends on how rich data you have and what is available for you. You can include everything that you have. You can build this so-called input sentence, this input sequence of whatever information you have. In our case, we use age, gender, and social employment state, but you can also include health status at the particular age, or level of education at the particular age, or whether this person is giving a birth to a child at the particular age, or whether this person has a partner, or everything what you have you can use in order to enhance your model. I hope I managed to reply to your question. If not, we have Alessandro Spata here with us as well, and he's an expert at writing the code and helping to develop this model technically. If you are eager to hear maybe more technical details, I think Alessandro would be happy to share with you more detailed aspect, because he has prepared a couple of slides. So let me know if you want to hear more about that.
Yeah, I hope to know more about the transformer details. Yeah, if you could illustrate more, I would happy
Yes,
to.
then Alessandro, how
Okay.
are you doing? Maybe you could try share.
Yes, we can. Linda, can you show the last slides?
I can, but also you can share your slides, I think. But if you prefer that I share them, it's not a problem. All right. Then,
Okay. So thank you very much for the question. In this slide, we actually don't go into details, but we show the input and output we use in the model. So we start from panel data, where each person is identified by a ID. And for example, each person has this data, the gender, year, age, and the status. The first variable are used as predictors, and in order to forecast the status that can be student, employed, pension, and so on. So these are our initial data. Next slide, please. And these data are split into training data, validation data, and test data according to classic machine learning methodology. Next slide. So what is the element of novelty of this method? In a traditional machine learning model, each predictor is used as a single input. For instance, if we want to use a neural network or a LSTM network, we have to prepare data in order to have for each predictor and for each regression of the predictor an input. Here we can have the gender, it doesn't change over time, the year of the observation, the age, the previous value of the status, and in order to predict the status at the time I+1. That means to forecast the next value of the status. This is the traditional machine learning methodology, and this is affected by missing data. If we don't have all these data, we have to fill up, or we have to select only data without no missing value. Next slide, please. The element of novelty of this method is that instead of giving an input for each predictor, all the predictors are collected and coded as a sentence. Technically, it is a string, an input string, where we concat all the predictors. And this will be the unique input of the transformer architecture. Based on this string, we forecast the status at the time i+1. And the transformer architecture is very known in literature. We suggest to start with the paper "Attention is all you need." You will find a review of encoder-decoder architecture and the introduction of the attention mechanism. And we don't go further into details in this webinar, but you feel free to contact us for any technical details. Thank you.
Okay, thank you for the question and for Linda and Alessandra's explanation. The next question is from Ding Rui. And since the question has been inputted in the chat box, so I will just read this question for this question raiser. So the question is, thanks so much for your presentation. And my question is about the time preparation of conducting transformers. So i.e., how much a researcher needs to master this method if he or she just have basic training in statistics and merely can employ easy models. So I think this is a practitioner who want to use this model. So Linda, could you please answer this?
Yeah, thank you for the question. I must say that I am at the when I started doing this method, I was at a very similar stage. I am social scientist by training, and I'm not a computer scientist, and I'm not able to code a model myself. However, our approach was to use all the internet resources that are available, and when we started developing our model, we found an example on the internet, and then we just started building on this example. And in our case, just to be honest, it took quite a lot of time to figure out how the model works and then how to deal with it, because it becomes a bit more tricky when you are predicting a sequence instead of one outcome. Because let's say if you are using a preceding sequence to predict a binary outcome, let's say whether a person will have a child in the next year or not. And when you test how model predicts, it is very easy. It is either yes or no, and you can very easily quantify how well model predicts. However, it becomes tricky when you predict a sequence, because how do you determine then how well the model works? Is it good if it doesn't predict correctly 1 year? And does it matter whether the 1 year that was predicted wrongly was the first in the sequence or the last one? Or what does it mean when you incorrectly predict 2 states, or if you predict employed instead of marginally employed? So you have to come up with a methodology how you actually evaluate this sequence accuracy. And I think this was the most difficult part for us, which take most of the time. It was not actually so much the technical part of running the model itself, because you can take the code from the internet and prepare your data and do it, and it might take some time, but not enormous time, to prepare the data and to run the model. But the tricky part comes when you start thinking, actually, what do I do with these predictions? What does it say? What are the implications for theories that we have that we know and that we have so far? So this part was the most time consuming, and for that one you don't really need like explicit technical things. It's just about your creativity.
Okay, thank you, Linda, for the response. And actually, the next question is highly related to your response to the previous question. The next question is from Daria Frost, and the question is, could you elaborate on why you use so few predictors? At this stage, it seems that you are quite effective at predicting stable employment, but less accurate in other scenarios, likely because the model lacks key factors that might indicate what could go wrong. For example, I suspect that the prediction results for non-stably employed clusters could vary with the inclusion of health status at age 56 or family status.
Yes, thank you. It is a very relevant question. So there are several reasons. First reason is the data limitation. It's just the data that we have at this point, which is rather easily available to us. And with this data, we have limited information. This is the reason number one. The reason number one, we actually decided that we will take it as an advantage rather than disadvantage, because we wanted to just to try actually how much data we need in order to make decent predictions. And if we would assume that, let's say, policy regulators would decide to use this model to improve their ways how they target their policy when they prepare their policy recommendations, it would be easier if you have in a rather simple model for which you have rather little data available, because these fancy register data, it is not so easily available in all of the countries. And the simpler data you have, the less information you need in order to do predictions, the better actually it is. So our passion was to use as little information as possible to build as good model as possible. And I totally agree that if we would add information about the health status or profession or education level, I believe that we would build like a monster that would be able to predict everything, which is kind of scary. So I can clearly see that adding more information would very much improve the results. But for now, this is with what we started, and yeah, we are quite happy with it. And there's clearly much more potential to it.
Okay, thank you. Any other question from the audience? Since I haven't seen the more questions from the audience, let me take the privilege as a moderator to raise my questions. Actually, a lot of my questions have been included in your last slide about limitation. They have clarified, so you omitted the limitations, so I do not need to ask them. But there are two additional points that I want to highlight. One is about the comparison with the other methods. So you have already compared the findings based on transformers with two other methods. One is you use one time point to predict the following 5 years, and the other is could you please remind me the other?
You probably mean Markov chains.
Yeah.
Where you use the current state.
Yes, exactly. One is the previous state to predict the next. The other is you use 1 year to predict the following 5 years, right? So from my perspective, that is a little bit unfair comparison, because as you can see, the transformers have exhaustively used all the informations of a person's previous life course events, right? So all the sequence information.
Yes.
But the two comparisons only use very limited information from that chunk of information.
Yes.
So the result, it is not that fair comparison to some extent, because you are not using the same level of amount of data, right? So your model, the model that use transformers have used much richer data than the other two models. So this is my first question. So regarding the comparison results, since the comparison per se, to some extent, is not very fair comparison, considering the data that they have each utilized, so the results are not that fair evaluation either. And related to this, I was wondering, why don't you compare your findings or prediction accuracy with some models, not using transformers, because if you use transformers, to some extent, you are adding another layer of intricacy here, which means that, so for example, why do we use natural language model? Because natural language is so hard to analyze, so we need to vectorize it, right? To transform it into data, 1, 2, 3, 4 numbers, right? But when you use transformers, actually you are trying to transform one highly well-organized data set into sentence. That adds another layer of intricacy here. That's pretty tricky. So I was wondering, so how about very simple machine learning models, but I use all this data to make a prediction? Rather than compare with the two methods you have selected, just use very simple machine learning model, what type of algorithm, but with the same level of data richness. So what would the result be? This would be my elaborated first question. And my second question is similar to Daria Frost question, the previous question. That is also related to your response to that question. That is, I'm thinking about the application. You are right. The application of this method is a little bit tricky to select because it has some assumptions. To make accurate prediction, to some extent, we need to have the assumption of stable societal changes. So for example, we can imagine that if we use all this life course sequence to predict a person's next life course sequence, and we are using all this information, we are assuming that there is a stable social environment here so that we can make correct prediction. But if the social environment, if there are some exogenous shocks like wars, pandemic, right? And everything can change. So this model, it seems that it cannot account for those exogenous shock that happen in a society that changes a lot of people's life course events. Yeah, these are my two questions.
Thank you. Very relevant questions and very good points. So regarding, why do we compare to these particular methods? That's a good point, that if we are very honest about it, they are very different approaches, because one uses exhaustive amount of data while the other just a little bit of data. And it is true. Maybe I need to mention that when we started this project, we started with simpler machine learning algorithms that are designed for sequence predictions. We started with a very simple feed-forward neural network. And then we tried also LSTM, which is long short-term memory algorithm, which is also a neural type of algorithm. So these machine learning algorithms are the ones that are designed for sequence predictions. And when we were using these methods, and then we discovered transformers, we compared all these three methods. And what we determined is that actually results tend to be close to identical. However, the big advantage of these other machine learning algorithms that use exhaustive amount of data, like for example, LSTM, they take a lot of time to train the model. If we use transformers, we need, with good servers and with good GPUs, we need a few hours and the model is trained. Well, if you use a method like LSTM that works on a very similar logic, it takes 3 times or 4 times more time to train the model, because
so the efficiency is higher to use transformer.
Yes, transformers is much more efficient because of this architecture that it has, and because of this self-attention mechanism, which allows also parallelization, whereas in this regular recurrent method, you would always calculate the previous states, then you would take the next, then you again calculate the previous ones, then you again predict the next. So there is a lot of intensive calculation happening, whereas with transformers, it's enough to determine this relationship once, and then you just use these interdependencies that you have calculated. So yeah, transformers is much more efficient. But yeah, you are right. I think maybe we need to think about it and mention it more explicitly why we decided to compare to these particular methods. Thank you for this point. And then regarding these exogenous shocks, yeah, you're totally right. These things are happening, and of course, model is not able to predict like some random happenings. However, what I can say is that these things are happening all the time throughout history, and we are using individuals born between 1940 and until 2000s. So actually we are covering a long range of history, and during this time there were many things happening. For example, in Europe we had war during this period, and there were several economic crises. There was a very high inflation, which was economic crisis, then economic crisis in 2008 and in the 90s. So actually it's kind of implicitly already like inserted in the model that there are these one-off events that may happen, and despite those, still model is able to catch up these major patterns. But yeah, of course, this is one of the limitations, that you cannot really predict these one-off effects. But yeah, what you can do is you can retrain this model afterwards when this crisis has happened, or compare the outcomes of this crisis, how it affects the model prediction capacity, to how it works when you take another crisis that happened in the past and then compare these outcomes. So you can you can calculate it, you can analyze it, and then you can make some kind of assumptions how badly or how good or bad these events impact the functionality of the model. So, but yeah, this aspect is always present in machine learning algorithms in whatever predictions you are doing, unfortunately.
Okay, thank you, Linda, for the response. Is there any other question from the audience? Okay, I think there is no more question from the audience. So thank you, Linda, for today's wonderful presentation. I think this is a really creative and innovative application of using transformers to do demography research. And thank you very much for giving this talk. And thank you all for attending today's webinar. Okay, so see you.
Thank you so much. I enjoyed it a lot and wish you a nice evening. Thank you for inviting.
Thank you.
Thank you.
Goodbye. Goodbye.
Goodbye. Thank you, Alessandra, for
Thank
your
you.
participation as well. Bye.
Thank you. Bye.